thanks. Yeah, my name's Clark. Can everybody hear me, by the way? Yeah. Cool. Yeah, today we're going to be talking about some of the work we've been doing recently at Fast Radius and building the factory of the future. And just kind of want to lay out some talk goals before we get too into it. A lot of this talk is actually going to be sort of history and setting some context. This is something I'm kind of fond of personally, and sometimes it's just nice to reflect back on what our community is and sort of where it's situated in history and where we come from and why we do what we do. So I'm going to talk about that a bit. And then I'm going to talk about some of our experiences at Fast Radius and where we think that sort of fits in to the timeline. And then some reflections about some stuff we've learned along the way so far. So just a quick tidbit, Fast Radius is a company. We're in Chicago. And what we do is we do production quality 3D printing manufacturing. I'll tell you more about that later. But for context, we're about 50-ish people and a pretty small team, and actually a pretty new team. Dev work in earnest really only started last summer, and we've been really busy, and we're really excited about what we've been doing. Yeah, so let's get into it. I wanted to talk a bit about manufacturing. That's what we do, is we build stuff, and I kind of want to set the stage for that. Manufacturing is the art of building stuff, and it's a very technological process, but it's not just technology. It's not just the actual stuff that's making the physical product at the end of the day. It's also the process around all that stuff. There's this constellation of other technologies around that. And I think that manufacturing and information technology advancements have really sort of been linked in lockstep throughout history. I kind of want to share why I think that is. But another speaker I'm really fond of likes to do a dictionary definition, so I thought I'd add one too. So this is produce, and it comes from the Latin meaning to lead forward effectively. And it means to create or form something as part of a physical, biological, or chemical process. And I'll get back to this, but it sort of links in with Elixir. This is a clay tablet from around 2300 BC. And I think this is really awesome. First of all, it's awesome that we have something so old. It's just cool to look at, that somebody else's hands touched that, almost 5,000 years ago. And what it is it's an account of barley rations issued to adults and children, written in cuneiform in ancient Sumer. And why is this interesting? I think it's interesting to think about this as a piece of technology. And writing was not always something that existed. I think it's really easy to forget that. What we do as programmers is effectively incredibly high-level writing. And it's easy to forget that that didn't always exist. Writing had to be invented, just like everything else had to be invented, like Elixir had to be invented. And it came about, a lot of historians think, in response to other innovations that were happening around this time, namely agriculture and sort of a system approach to raising animals and harvesting crops. Going forward in history, skipping a couple thousand years, this is in the 1700s and in France, and these are artillery pieces. And in the late 1700s, a French general by the name of Gribeauval was tasked with sort of revamping French artillery. And he did something interesting as he was doing this. He didn't just take what they already had and made it a little better. He kind of changed it in a really subtle but systematic way. He started to task all of his artisans and builders with building these artillery pieces in a way such that they were interchangeable. This meant that if something broke, you could swap out only the piece that broke with a new one, And this greatly shortened delivery times in case something broke in the field. It also lowered cost dramatically. And this idea sort of transferred to one of his subordinates who was tasked with doing this same process but for muskets. And so this gentleman, Honoré Blanc, carried out this process of sort of attempting to break up the musket into its constituent parts. This sort of subdivision of this is the stock, this is the receiver, this is the trigger housing, such that they could be produced independently. And again, I'm going to hammer on this theme. This idea didn't always exist. This idea to separate things so that you could understand them individually and then form them into a constituent whole really came about not all that long ago in our history, really in the 1700s. And Blanc did one other thing. He noticed that when you had all these constituent parts, you wanted to be able to tell, is this one a good one? It's been made by somebody a couple hundred miles away. It got shipped to us. We want to verify that when I plug it into this musket, it's actually going to work. So he came up with this idea of a master. And so this is a part that you would make that represents a known good piece. And then you take the piece that you've created and you compare that against the master, and if it matches up, it's a good piece. And so you think about this, it's not an especially difficult thing, is it? It's not that weird. But it's a pretty fundamental information change about how you conceive of the information and how you manufacture things. It's not really a manufacturing innovation so much as it's a different way of thinking about information as it relates to building something. We know this idea of sort of a master comparison ideology as testing. We do this all the time. We say, if this thing works by this exercise method that I've given it, then it looks good, and we can put it into production. We've verified that the instance of whatever we're making works, and it's good. A ton of other stuff came out of this innovation of this master. Namely, you have to start being able to measure stuff. If you're going to ship stuff across distances as small constituent parts, you want to have some idea that not all of them are going to be rejected when they get there. So measurement has to really tighten up. You start to form standards bodies so that you can all come up with the same way of measuring stuff. Because maybe your way of measurement works, maybe your way of measurement works, but they could be different in subtle ways. So you start to see these sort of information technologies and groupings forming around manufacturing in an effort to increase the quality, lower the delivery time, lower the cost. Still in the 1700s, this is a steam engine. And the steam engine really started to become a reality in the mid-1700s, but was first invented in the early 1700s. And the steam engine is probably the prototypical example of what you think of when you think of the Industrial Revolution. It's this thing that's, it can do the work of however many people. It doesn't get tired. It can run at all hours. And it doesn't take orders. It essentially just does whatever you want it to do. And this is huge. This has the effect of massively lowering costs, increasing the breadth of what we can actually build. Another key innovation is that you can start to move production away from rivers. So prior to this point, prior to the steam engine being commonplace, production was really tied to water for a few reasons. The first is that water power is really cheap. As long as there's water, you can power your mill or an axle to turn to sew something, stuff like that. But also, rivers are great for their logistical ability. And so whenever you want to move materials to or from your mill, for example, you can just put it on a boat on the river, and that's it. Your transportation mechanism is effectively linked to your factory in lockstep. And as long as there's a river, you have a way to transport things, and you don't have to think about that as much. And the steam engine sort of makes that no longer the case. you can start to build a steam engine effectively wherever you want, in the center of a city, for example. You can build a lot of steam engines right next to each other. You can start to draw people to those steam engines and those factories. And so you start to run into more information challenges, right? You start to have to house these people. You have to start to build a shipping apparatus that doesn't rely exclusively on water. You have to start to be able to take into account stuff like supply chain. You have to project out how much capacity you have for a given time, how much fuel you're going to need, stuff like this. And folks did start doing that. In the 1700s and 1800s, they did start to do what we know as modern, industrial engineering. And they started to design these supply chains. They started to think in terms of shifts of labor, in terms of queuing theory, stuff like that. A lot of this stuff started to be invented around that time. And what you're looking at on the slide here is a log table, a logarithms table. And this is a really funny invention that we have no use for today. But at the time, if you wanted to do some specialized calculations around engineering, statistics, shipping, queuing theory, stuff like that, you had to look up effectively these constant values from this table in order to do some of the more complex trigonometry stuff. And as you can tell, this thing is basically, it's either printed or it's produced by hand. And if you imagine a book of these things, of logarithms, pages and pages of effectively a constant lookup table, what do you expect to be there? Errors. People get this stuff wrong all the time as they're putting together these calculations. And it starts to become really difficult to actually know and verify that, if you're an engineer working on the latest widget at your factory, that the logbook that you're using is correct. And so a ton of mistakes were made, and this was really frustrating for a long time. And one guy in particular was particularly frustrated by this idea. This is Charles Babbage. And Charles Babbage lived in England and the UK in the 19th century. And he was an inventor, a creator, sort of a tinkery sort of guy. He was always up to something. Really a polymath. He contributed in material ways to all kinds of sciences, railroad science, cryptography. But the connection that I'm going to draw here is that he was really interested in manufacturing and factories. And so he sort of would go on factory tours and he would notice stuff that he found inefficient and make notes of it, publish his findings, and further this notion of industrial engineering. But he also noticed stuff like the previous slide in these log tables where they were, hideously error-prone and all over the place, and they were very difficult and time-consuming to produce. You get a whole team of people in a room to produce one, and it would take months. And he thought, well, what if there was another way? What if we could make a machine do this? We've effectively figured out how to do this, sort of the rote method for doing it. What if we could make a machine do this? And he has this idea to create what he calls his analytical engine. And the analytical engine, as we think of it today, is incredibly primitive. But really, its design was the design of the first Turing complete machine. You had distinct sectors of memory for data. It was programmable. You could store procedures in it to do specific calculations at a later time, outside of the definition time. And you had control flow. This was the first machine that would have been capable of doing loops, right? And so this is kind of amazing. This is in the 1800s. And it's to solve something around calculating efficiencies for factories, solving engineering problems. And so you see this follow-on effect yet again of we've identified sort of massive technological advancements in physical goods and manufacturing, and then a follow-on advancement or a related advancement happens to information technology. And so this is the first Turing-complete machine. And so what do you do with a Turing machine? You want to program it. You want to do stuff with it. You want to write programs. This is Ada Lovelace, and many folks consider her to be the first programmer who ever lived. She wrote a program for Babbage's Analytical Engine to calculate a sequence of the Bernoulli numbers. And it's not too important what those are, but it's stuff that you would have to do pretty tediously by hand. And she wrote a program to do it, and it looked like this. I believe this is actually the original to calculate the Bernoulli numbers. This is known as Note G. And like I said, she's considered by many to be the first programmer. But just as a little aside, I know she was the first programmer, and I'll tell you why. The machine she wrote her program for was never built. So Ada Lovelace was the first person, the first programmer who ever had her project canned before it got to production, right? So that she's definitely the first programmer. Skipping ahead a couple hundred years now, we're in the 20th century. It's World War II. The assembly line has been invented. And we're figuring out how to use it to make all kinds of stuff. This is a plant, actually in Texas, I'm not exactly sure where, but it's around here, of B-24 Liberators, which were one of the main planes flown by the Allies in World War II. And we figured out how to do this assembly line thing, and it has a similar effect to a lot of the other stuff I've described so far, in that it massively increases efficiency yet again. And accordingly, we have an even poorer idea of how to manage it. And so we have to start to develop those technologies around how to control this thing. These ideas of one person doing one small bit of labor on one separate part, passing that on to another person doing another bit of labor on a different part or modifying that part in some way. You need a way to track all of those steps of work. You need to be able to plan through this entire massive line, what exactly everyone's going to be doing, how long it's going to take them, what they need to do their job, what happens when they break something, what happens when they fail, what happens when we run out of fuel, et cetera. You have to start planning for these contingencies. And the complication here is immense. And so we start to invent stuff to do this. You basically have to invent the database to do this. And you start to see companies around this time come up devoted to punch card computing and tabulation and things like this. Basically furthering Babbage's ideas around the analytical engine in a sort of a more refined way. And World War II changed the world for a lot of reasons. There was a massive, massive investment in technology for obvious reasons. But I think it helped us all be in this room today due to this man. And this is Alan Turing of the so-named Turing machine, who helped crack the Nazi Enigma encryption mechanism. And he did this, one, he was a genius, that helps, but also through subtle application of information technology. And he invents sort of the modern electronic programmable computer in the process, and gives us this mental model for what we mean when we say whether or not something is generalizably, or I guess generally computable. That's why we call it a Turing machine, is he sort of formalized the mathematics around this idea. And this is in the 40s. And so again, we're sort of marching forward in history. But one thing I would call out here is that if you take the events I've described so far, they really are starting to stack up in time. More of them are starting to happen closer to today. This speed of progress is starting to increase. And it happens, it keeps going. Now we're in the 60s and 70s. And all this investment in the war machine in the mid part of the 20th century has sort of carried over into, well, we have all this stuff, what do we do now? And so a lot of labs are formed to study this stuff in more detail in peacetime. And one of the crucial things that comes out of this is the ARPANET. And the history of the ARPANET as a concept is sort of debated as to whether it was just purely experimental or whether government influenced it as a means of creating a communication network that was resilient in the face of nuclear attack. So yeah, it's 1972. We were under the idea that we could be attacked with nuclear weapons at any time, but the history there is a little suspect as for what actually the impetus for the ARPANET is. But in any case, we start to connect computers together across long distances. And nobody quite knows how big of a deal this is. They all kind of have a feeling. They're like, it's great. We can send a message from MIT to Stanford. We can say hello. But the facilities for doing this are pretty primitive. And sorry, just an aside, I noticed that there's an AWS in the middle of that. That's kind of scary. What does Jeff Bezos know that we don't? This is kind of the original fault-tolerant network. And it sort of comes about by accident, sort of comes about in response to a need. We're not sure, but in any case, it comes about, and we're here today. And now I want to take us a bit into the present day. So this is about 40 years after the ARPANET. This is a RepRap. This is an open source 3D printer. And you may know 3D printing, but if you don't, my quick 2-line explanation of what 3D printing is it is the selective application of raw materials to form a solid. And you can think of it in contrast to the other ways that we produce stuff, which is namely mostly subtractive methods. So you'll take, for example, a raw block of aluminum, and you'll basically, using a computer-controlled machine, you'll mill out parts of that block until it looks like what you want. But it started out as a raw block of stuff, and you end up with a lot of stuff on the floor when you're done. Additive manufacturing and 3D printing are sort of the opposite of that. It's adding material only in the exact precise place where you want it. And this picture is interesting mainly because somebody was able to build this basically on their desk. So it shows that 3D printing has reached this level of interest that folks without a lot of resources are able to approach it. But it's also interesting because this picture could not have been taken any time other than in the last 10 years. 3D printing is absolutely brand new, and it's really incredible. It's this incredibly recent technology that's really only started to become mainstream in a way because the patents for the main 3D printing mechanism expired in 2009. And so you may know this machine. This is a MakerBot. This is a super common machine. You can go out and buy one of these for a few $100, and it's amazing. But prior to 2009, you couldn't do that. They were patented. But the technology was originally invented years before. I think a lot of people have this image of 3D printing as this sort of prototype technology. Maybe your friend has one. Maybe you have one. Maybe you like to produce, little figurines or jewelry or stuff for your house in it. Sure, it's fast and convenient, effectively, but it's the quality is low, right? You wouldn't really trust this in something serious. And this has been true really until about the last 5 years. And there's been a generational advancement in 3D printing tech, sort of similar to the prior advancements that we saw around artillery and around the steam engine, where the consistency and the engineering properties of the printed parts is now meeting engineering standards for real applications. Think parts that are strong enough to put in your car, parts that are strong enough to go in a plane, parts that are durable enough to go in your hip, in your kitchen, wherever you can think. And so what's the point? The parts are better, but what does it mean? It means a couple of things. It means that you can now produce things that you used to never be able to build. 3D printing is really unique in that it can actually physically form things that you could not physically form by subtractive methods. For example, things with large voids in them, so like a hollow space in the part, very difficult to form via a CNC mill or injection molding. And it means that the skill required to produce this stuff has also gone up. If you want to produce an engineering quality mesh lattice, like my coworker is working on here, it's not as easy as just opening up your MakerBot software and slamming in something and printing it out and expecting a large aircraft manufacturer to throw it on their plane. The expectations have risen along with the quality. And this is kind of the stuff that I get to work on. Our team is building tools to support this process, to support the folks who are doing the actual mechanical engineering to put this stuff together, to help you get apart from sort of this raw information, which is how all parts start. It starts as an idea, and then it becomes a computer-aided design drawing, and then it becomes a printed part. And it changes stuff in another really fundamental way, in that it completely shakes up what we think of as logistics or supply chain information. And I want you to think for a second about how much stuff you order on Amazon. If you're like me, you probably order quite a bit of stuff on Amazon. We all probably do. Amazon's doing very well. And then think for a second the next step. Where does it come from? Where does that stuff come from? How does it get to you? How many trucks does it live on until it gets to your door? How many planes, ships? How many warehouses does it sit in, and for how long? You don't have a precise number in your head, but I bet you're thinking, wow, it's actually quite a bit, because it is quite a bit. It touches a ton of modes of transport before it gets to you. Most of the stuff probably doesn't even originate on this continent. It probably crosses at least one ocean to get here, which is incredible. But imagine what would happen if, instead of warehousing all that stuff, we just built it as soon as you ordered it in a location that was near you. That's convenient for you, so you like it, I like it. The delivery time goes down, it gets to my door quicker. But it also does other stuff. It saves on warehousing. So all those Amazon warehouses that you drive by on the freeway, those start to get a little smaller and a little less necessary. It saves on shipping. Think about how much carbon shipping stuff from Asia costs on an annual basis. It's a ton. And so how much can something like 3D printing really clean up supply chain? And this is kind of the problem that we're attacking at Fast Radius. So this has been a really long-winded way of getting to this point, but there's a ton of work that goes into this idea of something so fundamental as trying to shake up manufacturing and supply chain at this level. And we're attempting to attack that. Our shop is a full production shop, and we do everything from your idea to the production of that part to QAing and making sure that that part is what you wanted it to be, to fulfilling it to you. Unfortunately, you do have to ship it at this point, but we're working on that. And it's this enormous information challenge. I want to stress that. The fact is that right now it's massively logistically complex to do stuff like this. And transitioning away from the current mode of supply chain fulfillment towards something where 3D printing plays a larger part is massively complex. It doesn't happen overnight. It's not a switch flip. And you have to design and condition behavior around flipping this switch. And it's not quite a reality yet. And I kind of want to talk a little bit about why. So Alan Kay has this great quote about in computing, there are many, many instances of roughly 30-year lags from when an idea was really proved out to when it gets generally accepted. I think this is a fascinating idea. If you look at it, it really speaks to fashion and sort of this information propagation in society rather than speaking to any specific technology, right? I bet everybody in here has actually already thought of something where they know this is true. Something where in the past we knew that it was good, but then it took quite a ways to actually make it to us. So some examples, cell phones. Owning a car in the early part of the 20th century. Getting in a stranger's car as if it were a taxi, just because there's an app that now says Uber on it. I think everybody can probably remember that there was that time period where you probably knew one friend who had a cell phone, right? It was kind of a weird thing. And then it ticked along a little bit, and then it seemed like everyone had one. And it seemed like there was just this sort of like the bubble popped, and it went from like this 10%, 15% mark to like the 95% mark in the span of like 4 years, maybe. And I think there's another technology like this that I think we're all a little bit more familiar with. On the left is the SLA-1. So this is one of the first stereolithography 3D printers. And it was created in the late 80s. And on the right is the first Erlang interpreter. And I think when you look at these technologies, they both really happened around the same time. So 3D printing is really coming up in the mid-'80s to the late '80s. And the SLA-1 marks a point where it just starts to crack this point where it's something useful. And Erlang, when it started out, had similar detractors, similar vibe. Everybody looks at this and goes, great for prototyping, I'd never use this in production. Great for designing a switch, I think we'd need to rewrite it in C or Plex or whatever. But it occupies this space where a very, very small sliver of people are starting to do it. But everybody can sort of see that it works. So why isn't it caught on yet? And I think this is a weird coincidence, and I think that Elixir and 3D printing are actually unusually suited for each other. If you look at the weird coincidence of the Erlang 3D printing sort of timeline, they both have a few things in common. They're both radically new ways of imagining how you interact with information, right? On one hand, you are creating something from nothing, and on the other, you're throwing away all of computer science history to that point in order to program with a completely new model that you think is better and that you think allows you to not care about all that stuff like out of memory or dereferencing null pointers or having to use mutexes. And so they're radical departures, and it's actually fairly hard to sell them. And they also have this idea that things should be adaptable, things should be interactive. You should be able to do as many iterations of this idea as you want. And that process should be sort of convergent toward correctness rather than writing your Haskell program and proving it's correct, and then when you ship it, you know it's perfect. And it's like, the real world doesn't really work like that. So I want to tie this in a bit now to the Elixir side of stuff. So this slide should look familiar, namely because it's so similar to the previous one. So the previous definition we looked at was produce. This one's process. And we know a thing or two about processes. And I think it's funny that these two things have a fairly similar definition. It's a series of actions or steps taken in order to achieve a particular end. And we know all about that. A process is this single-threaded idea that helps you coordinate these disparate units of work. And it's phenomenally useful. And we take it for granted. But it's actually a pretty radical innovation. It's not how everybody else does stuff. It's not how everybody's been doing stuff for 50 years. It's actually pretty new in context. So I'm going to get to sort of more of the tech and like what we've been up to in my time remaining. So like many of you, the core of our deployment is a Phoenix app. And it's totally central to what we do. It runs everything for us. It helps us make sales, take orders, schedule and dispatch factory work, do quality assessment. It really is central to what we do, and it's rock solid. It sounds weird to say that about a piece of software, but we've really had no issues with it, which feels great. But there's a downside to that, and that there's a nearly 100% chance that when something goes wrong, I know it's my fault, and it's not Chris's fault. So thanks for that. And we like it because not just it makes us happy, but our users love it because it's fast as hell. And that's kind of what we care about is as you're building this factory, people run it. People are in it. People spend hours in it. And you want to make their lives easier. And when stuff is faster, those folks feel better about coming in early and staying late. And they do better work. And so we really like Phoenix for that. This is my little friend, the Toy Story alien. This is our favorite test model. And actually, a lot of our work that we do at Fast Radius looks a lot like this. Not as 3D printing, mind you. It looks a lot like, say, taking the 3D mesh file of the guy on the left and turning him into the screenshot on the right, so that our users can see a clever screenshot when they're scrolling through their list of parts for their next order. A lot of our stuff looks like this. It's the stuff that we all do. It's the generating thumbnails. It's creating PDFs for work orders. It's part complexity calculations. It's making sure that we're always up even when our third-party APIs aren't. It's shelling out to other processes that might work, might not. It's uploading big files and making sure that we retry if they time out for whatever reason. And Phoenix and Elixir has helped us sort of, in some ways, not care about that. We want to really work on mapping our knowledge to our domain and really enabling our users, not debugging Phoenix. And I can say that that's been true so far. This is a really common pattern for us. The notion of sort of having one thing find work and having another thing do that work. And this is kind of the essence of, if we can relate back to why Erlang is such a radical, Erlang and Elixir, such radical departures from previous ways of working with machines, is that you have this notion of separation. You have this idea that you want to have one thing sort of make an assessment about the world and have another thing do some work in response to that assessment. And if one crashes, it doesn't affect the other one. And this maps incredibly well to what we do in the factory every day. If one printer goes down, it shouldn't affect the rest of the printers. If our shipping and receiving is having an issue, we should still be able to print stuff, right? If customer orders aren't coming in, why can't we keep making parts? You get the idea. So I'll show you a little code as an example here. So this is I just copy pasted this from our code base. We have this notion of a work order, and a work order is sort of our mapping of what a customer wants. A customer comes to us and they say, I want 1,000 prints of this part. And our printers depending on the size of the part, won't fit 1,000 units. And so we have to break up this notion into smaller bits. And a work order is what we call that. And so this is just in the middle of sort of committing this action to the database. We, sort of about halfway down there, you'll see that we just render a template, and we broadcast out the data of that work order. And why is this important? This seems like a really tiny thing. It's crucial because it goes to everybody in our company whenever they're interacting with our work order system. Anybody who is working on the latest iteration of a design, now they see the most recent possible version of the work order without having to do anything or having to care about updating their data. It goes to the lab technician who's now post-processing, painting, sanding, that kind of thing, finishing the part for delivery. And they might see that, oh, the requirements have changed for this. I need to update what I'm doing so we can hit our delivery deadline. And this is huge. And this is sort of where we want to be. This is where we want our factory to be, is we want it to be this notion of everybody is able to see the same coordinated view of the world and not have to worry about whether the code is working, right? They have bigger problems to worry about. So we want to help them do their job better. And the barrier for entry for this is honestly about as much code as is on this slide, which is incredible. I'm very grateful for that. We also do other stuff, though. Phoenix is amazing, but we also do other stuff. We do a good bit of NURBS work. And there's been a ton of NURBS work at this conference, and that's awesome to see. And so I'm just going to pile on and say how amazing it is as well. So we deploy NURBS on Raspberry Pis to our factory floor to do stuff like telemetry collection. So we'll collect temperature, humidity, pressure, vibration. We also have our Raspberry Pis interact with our 3D printers in real time, polling them for their status, polling them for their operational metrics, letting us know how far along a print is, for example, or what the print queue looks like. And so we can show a real-time picture of our factory, not only to ourselves internally, but also to our customers who want to know, well, how's my thing doing? Is it actually going to ship? And customers love this, as it turns out. Customers are all about this. They know, they want to be able to see down to the hour when stuff shows up. And that's where we're going. And NURBS is helping us make that possible. So we've done that with some tools that a lot of you all have built. This is just a little echo of libcluster. And we use libcluster in a way that I thought was kind of funny. We use it to discover during development. So we'll deploy a Pi in our factory, a Raspberry Pi in our factory, and we'll also run it on our local machines. And we'll use it to discover the Pis that are out on the factory floor. And then we will connect to them. Justin showed an example of this as well yesterday, using the remote shell functionality, which just feels like cheating. You're just like, it shouldn't be this easy, but it is. And so you get onto the box, and you are able to say, why is that one printer not doing anything? Is it down? Oh, I can just send an HTTP request to that printer. They're all networked, of course. So we can just send a request to this thing, get some data back, figure out what the issue is, and go fix it. So here's an example of that. Just in the REPL, sending stuff to hardware. It's great. Of course, you get Observer, which we all know and love, and that's been invaluable for us debugging why the code that we wrote broke. So, because we do write bugs. This is one that I haven't seen around a lot, and I'm coming to the end of the talk, but I kind of wanted to share this one before we got out of here. The NURBS deployment infrastructure is amazing. But sometimes you want something a little finer grained, something a little bit tighter of a feedback loop. And so one thing we've taken to doing is, once we've found the Pi on the network, using some of the built-in Erlang, OTP, RPC stuff to do local dev on your laptop of the module that you want to then push out to your Raspberry Pi. And then Erlang has this amazing introspective ability, and so you can load the binary of that code, and then you can push that code off to remote devices, just that module. And so now you can say, I just want to load this code of this one module that I've changed and push it to our Raspberry Pis on the floor. And in that way, you have this amazing feedback loop where if you have the Pi in the REPL, or you have the IEX session for your Raspberry Pi and you've pushed code to it, you can develop something on your laptop, push that code in less than a second, it's there, and then you can immediately run it again. And I wouldn't recommend doing this in production all that much. I would probably stick with more of a NURBS hub approach, but this has been invaluable for us in doing stuff like figuring out new hardware. It's kind of like Lispy in that way. You want to be able to just ask questions of the hardware that you're working on, which we do a fair bit of hardware work. And so we want to, why is this temperature sensor flaking out? What's wrong with it? I'll just push a new version of the module and I'll ask it a question instead of, agonizing over, all right, are we going to have to take this thing down? Are we going to have to pull it in? Are we going to, how are we going to replicate production? It's like, nah, just get in there and figure it out. And I think we're all used to that, but it's a fairly radical idea in terms of manufacturing to be able to just go in and ask a question of something this easily. So I kind of want to wrap up, reflect a little bit here about where all this fits in. The toolkit that we have in this community is absolutely incredible with the work that everybody's doing. We're all standing, on each other's shoulders as we do this stuff. And that applies just as well to a lot of the Erlang core stuff with OTP. But you still have to design stuff. And this has bit us a few times, is that this stuff is not magic, right? It's tools. And in fact, it's incredibly powerful tooling. But you still have to, you really have to design this stuff as well. And I think you have to get bit by OTP a few times and sort of learn how to do things and how not to do things in order for it to be this thing that you really believe in. But it is amazing. And Elixir doesn't really do everything. And I think this comes up every so often when we're talking about it. But I think that's OK. I think we need to sort of lean into that. Elixir doesn't do number crunching. But what it does do is it integrates with everything else amazingly. And so we have Rust code in production at this point where it's incredibly easy to integrate into our Phoenix app because Elixir's facilities for starting and restarting that code when it fails are bulletproof. And so we don't even worry about it anymore. It's just this function that we call over here. And Elixir is great for this. And I'd like to just reinforce the correspondence between the advancements in the domains in which all of us work, because we all work in a bunch of different domains. Most of them actually aren't tech. Most of them aren't writing compilers or writing frameworks. And we're pushing advances in those fields. But there's a corresponding effect to how we need to advance our art in order to better support those advances. I hope I was able to illustrate that today. And I think it's my last one that I'm going to get to is just that we're people in history too. All the work that we do, whether it's a one-line patch or whether it's a new framework, is work that other people use and depend on. And who knows, in 50 years, 100 years, 200 years, that would be amazing. Somebody comes back and looks at some of the stuff we're doing, and maybe they take some hints from it. Maybe they take it, and maybe they push things forward with it. And I think that's about as much success as you could ask for. So just be mindful of that. That's about all I had for today. Once again, I hope this was cogent a little bit. This has been the Factory of the Future. My name's Clark Kampfe. That is my Twitter handle. And I work at Fast Radius. And I'll be around all day. Come find me.